Hey there, and welcome. Today, we are going to dive into one of the coolest and most powerful tools in all of mathematics, mathematical induction. Now, I know it sounds super formal, maybe a little scary, but the main idea behind it is actually, well, it's as simple as knocking over a line of dominoes. So let's just jump right in with a massive question. Let's say you've got a statement, a mathematical rule, that you're pretty sure is true for every single whole number out there. I mean, all of them. How on earth would you go about proving that, right? You can't test them one by one forever. It's literally impossible. So what do? I mean, just think about it. You could check if it works for n equals 1. Check. N equals 2. Check. N equals 3. Check. But that feeling of success doesn't last. Because what does that tell you about n equals 1 billion? Or a trillion? Or the number right after that? This whole one by one thing, it's a total dead end. We need something way smarter. And that smarter solution, this beautiful, elegant answer to an impossible problem, is all about dominoes. Yeah, seriously. Picture an infinitely long line of dominoes, stretching out farther than you can see. What are the two things you absolutely have to do to make sure every single one of them falls over? It really just boils down to two things. That's it. First, you have to actually push the very first domino. You got to start the chain reaction. And second, you have to know for a fact that if any domino falls, it's guaranteed to knock over the one right after it. If you've got those two things locked down, then the whole infinite line, it's going down. Okay, so let's take that simple domino idea and turn it into our mathematical game plan. Think of it like a 4-step recipe, a blueprint you can follow every single time to build a perfect, rock-solid induction proof. And here it is, the whole recipe. We've got the base case, which is just pushing that first domino. Then the inductive hypothesis, where we make a clever assumption. After that comes the inductive step, this is the heavy lifting, where we prove the chain reaction works. And finally, we wrap it all up with a conclusion. So step 1, the base case. This is all about just getting things started. All we have to do is show that our statement, our rule, actually works for the very first number, which is usually n equals 1. You just plug it in, check that it's true, and boom, the first domino has been pushed over. Now for step 2, the inductive hypothesis. This part feels a bit like a magic trick. We just state a big if. We say, okay, let's just assume for a second that our rule is true for some random generic domino way down the line. Let's call it K. This assumption is about to become the most important tool we have. And this is where the real action is. In the inductive step, our job is to use that assumption we just made about domino K to prove, mathematically, that the very next domino, k plus 1, also has to fall. This is us proving that the dominoes are spaced perfectly, that the chain reaction is real and it will not stop. And finally, step 4. You know what? This is the victory lap. Once you've knocked down that first domino in the base case and proven the chain reaction in the inductive step, you just write it down. You make a concluding statement that says, by the principle of mathematical induction, this thing is true for every number. Done. Okay, that's enough talk. Theory is great, but let's see this recipe in action. We're going to tackle a true classic, proving the famous formula for the sum of the first n numbers. Let's do it. First up, step 1, the base case. We check for n equals 1. On the left side, the sum is, well, it's just 1. On the right side, we plug 1 into the formula, so that's 1 times 1 plus 1, all divided by 2. That gives us 1. Hey, 1 equals 1. It works. The base case is solid. Our first domino is down. On to step 2, the inductive hypothesis. This is easy. We just state our assumption. We're going to assume that this formula is true for some number k. From this moment on, we're treating this statement right here as 100% factual. And now, the main event, step 3. Our goal is to prove the formula works for the very next number, k plus 1. So what you see on the screen is our target. This is what we need to prove is true. Notice the right side is just the original formula, but with k plus 1 swapped in wherever we saw an n. So let's get to work. Take a close look at the left side of that goal equation. The entire key to this whole proof is buried in there somewhere. Where is our assumption from step 2 hiding inside that big long sum? Do you see it? Ah, there it is, right at the beginning. That whole chunk, 1 plus 2 plus 3, all the way up to k. We know what that equals. Our step 2 assumption tells us it's equal to k times k plus 1 over 2. So we can just swap it out. We substitute it right in. This is the big move, the leap that induction lets us make. And from here on out, it's just a little bit of algebra. We just need to clean this expression up. Let's get a common denominator, then we can pull out that common k plus 1 factor from the numerator. We rearrange it and, would you look at that? It simplifies to exactly k plus 1 times k plus 2 over 2. It's a perfect match for our goal. We did it. And that just leaves the easy part, step 4, the conclusion. Since we proved the base case is true and we proved the inductive step is true, we can now confidently say that by the principle of mathematical induction, our formula is true for all positive integers, period. Now, this 4-step recipe is amazing, and it's not just a one-trick pony for these summation problems. The real beauty of it is how flexible it is. You can use this exact same logic for completely different types of problems, like proving things about divisibility or inequalities. For instance, what if you want to prove that n cubed minus n is always divisible by 3? Same logic. The base case is a breeze, since 0 is divisible by 3. The really clever part is in the inductive step, where you rearrange the algebra to find your original k cubed minus k term hidden inside. Since you already assumed that part's divisible by 3, you just have to show the leftovers are too. Or, how about for inequalities, like proving 2 to the power of n is always bigger than n? It's the same dance. You start by assuming it's true for k. So, 2 to the k is greater than k. Then, use that little nugget of information to build a clever chain of logic that proves the k plus 1 case must also be true. It's really slick. So, let's just zoom out for a second and think about what we've really done here. Mathematical induction isn't just about following steps in a recipe. It's a really deep and beautiful idea about how logic itself works and how you can chain truths together. And really, this is the whole point. This is what it all comes down to. With just 2 simple, manageable steps, proving the very first case and proving the chain reaction, you have the power to prove that a statement is true forever, for an infinite number of cases. You've basically tamed infinity. And that just leaves you wondering, right? This incredibly simple idea, this little domino trick, can solve infinite problems. It makes you think, what other huge, seemingly impossible problems out there in math, in computer science, or anywhere else are just waiting for the right line of dominoes to be set up?